Good morning, everyone. Today, I'm excited to share insight from a project focused on ensuring the performance of technology that has become ubiquitous in our homes. The robotic vacuum cleaner. While this device offers immense convenience, their core functionality, precise motion control, present significant engineering challenge, and uncompensated robotic vacuum or any automate system for that matter can struggle with accuracy, speed, and stability. Specifically, we often see issues like excuse overshoots when changing direction, a wrong setting time to reach the desired speed, and perhaps most critical, most critically, uh, persistent steady state error, meaning its consistency fails to reach its target speed or position. Our project aims to tackle this very issue head on. We decided we design and implemented a likely compensator, a powerful tool in classically control theory. So significantly, so significantly improve the robotic vacuum motion control. Our goal was to achieve a measurable enhancement in its transient response, making faster and smoother, and drastically reduce its steady state error, ensuring greater accuracy. Over the next 52 let's begin by defining our plan in control system. This refers to system process we intend to control. In our case, is the driving motor and the associated mechanical component of the robotic vacuum cleaner. This can translate control signal into the actual real vehicle of the robot. For this project, we model our planning using a hypothetical third-order transfer function. With 1 real 0, our specific formula is 50 multiplied by s plus 2 divided by s plus 1 multiplier s plus 3 multiplier s plus 5. This model features three real poles as -1, -3, -5, and real 0 at -2. These parameters were chosen to represent the system with current inherent characteristics. Upon evaluating the original uncompensated system as highlighted in the infographic, original system key for section, we found a critical baseline performance metric like original percent overshoot is 17.54%. I can run this for showing it. This the original system. Have percent overshoot is 17.54%. Setting time is 1.1 second. As the distance error is 13.04. This brings us to the fundamental question. Why do we need this? Why do we need a compensator? Reinforcement theory illustrate the limitation of our original system. Particularly is 17.54% overshoot and the persistent 13.04% steady state error. These issues cannot be solved by simply adjust the system gain. Why? Increasing the system gain might reduce the steady state error. It often comes at the cost of stability, potentially introducing even more oscillation or making the system unstable. Conversely, decreasing gain for better stability would make the robot even slower and less accurate. We need a more sophisticated approach. Our root analysis of the original pen clearly illustrate this limitation. As you can see, simply adjusting the gain cannot move the closed loop pole to the region that simultaneously satisfy or our desired performance criteria, especially the stringent steady state error reduction and overshoot control without compromising other aspects. This is where the lead compensator become indispensable. Is the original รูปแล้วครับ So what basically is a lead compensator? It requires a combination of two distinct types of compensator, each addressing different aspects of system improvement. Is typically inserted in the forward part of our feedback control loop, as shown in the infographic solution flowchart. Right? This first, we have a the lead compensator is primarily low is to improve transient response, making the system faster and more stable. It's achieved this by adding phase leads at higher frequency, effectively increasing the system bandwidth and improving its phase margin on the load lookup. A lead compensator pulls the load lookup to the left, shifting the closed loop pull into region that provides a faster or more damped response. Second, we have lag compensator. Its main objective is to radically reduce the steady state error and enhance accuracy. It does this by increasing the system gain at very low frequency without significantly impacting the phase margin at the gain crossover frequency. On the root cast, a compensator introduced a pole and a zero very close to the origin, which effectively boosts the low frequency gain, leading to the small steady state error for step input. By combining these two, the lag lead compensator offers powerful synergy, allowing us to simultaneously improve both the speed and stability of the transient response, while also achieve high steady state accuracy. It's about finding that optimal balance. Our design process as outlined in the infographic involve analyzing the original system, defining aggressive improve target, and then using automatic tuning to design the final compensator. This the gain margin and the phase margin. This is the improvement, send overshoot, setting time, and steady state error. This step response before and after. Why manual design methods are invaluable for understanding finding the absolute base compensator parameter for complex objectives can be incredibly time consuming. This is where automatic tuning come into play. We leverage MATLAB F bin search function, a numerical optimizer to find the optimal parameter for our lag lead compensator. The core of this automatic tuning is our additive function or cost function. This function quantifies how bad a given set of compensator parameters perform. It takes a compensator and 10 models along with our original system's performance and our ambitious improvement targets, and calculates a cost. This cost is where sum of square error between the current performance, like choose setting time, steady state error, and our desired target. Crucially, our cost function incorporates strong penalty. It heavily penalizes any compensator that lead to an unstable system or one that violates the fundamental pole-zero relation of lead or lag compensator. Most importantly, it applies significant penalty if the compensator system performs worse than the original uncompensated system, ensuring that the optimizer is always striving for unit improvement. Let's look at the result of this optimization. Right, the result KPI improvement, steady state, steady step response before vs after. Our percent overshoot reduced from 17.53% to 2.00%. That improve the setting time. Original is 1.1 second. Is reducing to 0.63 second. And as they said earlier, original is 13.04. Is reduced to 1.3. And we can see this. The first move for original system, the step response for the original. The orange is step response of compensated system. We can see that percent overshoot is less than before. And the bottom part is right here. Moving to the frequency domain, we assess the system stability and robustness using both port. A theoretic gain margin of 15 decibel and a strong phase margin of 55 degree. Both positive gain phase margin confirm that our compensated system is stable and possesses good robustness against variation in system parameters or external disturbance. The least component was key in boosting that phase margin, while lag component help maintain stability at low frequency while achieving that desired error reduction. In conclusion, this project successfully demonstrated the power of likely compensator design cover with automatic tuning, speed transforms, and other performing robotic vacuum cleaners, motion control system, into one that is significantly faster, more accurate, and robust. The likely compensator proved to be an effective tool for simultaneously addressing both transient response and steady state error. Challenge achieving a balance that is often difficult with simple control strategy. The automatic tuning process, guided by a carefully constructed objective function, allow us to efficiently find optimal parameters, pushing the system performance beyond its original limitation. While our current model provides a strong proof of concept, it's important to acknowledge its limitation. Our plan model is linear and simplified. Real robotic system exhibit complex nonlinear nonlinearity, like friction and model saturation. We also didn't explicitly account for wearing load or external disturbance. Thank you.